Welcome to a course on complex analysis. In the previous lecture, we have started our discussion on contours, that is curves on the complex plane. We are going to continue our discussion and we will see contour integrals also in this lecture. Now we are going to continue our discussions on the topic contours. That is, here we have made use of the parametric representation of the curves that we have seen. Okay, so the parametric representation is not unique. Okay, we can parameterize the given curves in as many ways that is possible. Okay, suppose suppose if you take t to be some function of tau, where this tau lie between alpha and beta, where this function phi is a real valued mapping. Okay, this is a real valued mapping which maps alpha beta, this interval alpha beta onto a comma b. Okay, of course this works when you give t in terms of tau, then the functions involving t will turn to involve the functions tau. Okay, now I may give you a diagrammatic representation of whatsoever the things that I have told you. So consider this to be the tau axis and consider this to be the t axis, right? And so let this point be alpha and let this point be beta, and this may be a and this may be b. Okay, we may have a curve which is from this point to this point. This is the point alpha comma a and this is the point beta comma b. Okay, either you may represent it, okay, you may parameterize it with the help of a function where the variable, whatsoever the variable that you take, be it t or tau, if you decide to represent it with the help of tau, then it ranges from alpha to beta. If you choose to represent it with the help of t, then it ranges from a to b. Okay, so this is the thing here, the continuity. Okay, just a minute. Here one more assumption has to be taken place, that is the function phi is continuous with a continuous derivative. So it means your function phi has to be continuous as well as the derivative of this function phi, that is phi prime, that also it is also a continuous. And further assume your phi prime evaluated at tau, that is like phi prime is positive for each tau. Okay, so if this is assumed, this ensures that t increases with tau. Okay, now in this case, then the function z, which is a function of t with a smaller than or equals t smaller than or equals b, transforms to z, which is a function of z of tau, okay, with alpha smaller than or equals tau smaller than or equals beta, and let me represent it with big Z. Okay, where big Z of tau is small z of phi of tau. Okay, so further we suppose, okay, this is another topic. Okay, like we are entering into another set of discussions, that is, suppose that the components x prime evaluated at t and y prime evaluated at t come of the derivative, that is z prime of t equals x prime of t plus iota times of y prime at t. Let me mark this as equation 1. Okay, this is the derivative of what? Of the function z of t equals x of t plus iota times of y of t, which is used to represent a curve C are continuous. So here we are talking about the continuity of the derivatives. Okay, that is x prime of t and y prime of t. These are continuous on the entire interval a smaller than or equals t smaller than or equals b. Okay, this is the supposition that we made. Okay, the arc C is then called a differentiable arc. Okay, if these suppositions are true, that is, your derivatives of the components are continuous in the entire interval, then the arc is called as the differentiable arc, and the real valued function absolute of z prime evaluated at z prime of t is absolute of x prime of t whole squared plus absolute of y prime of t whole squared, this quantity. This is integrable over the interval a smaller than or equals t smaller than or equals b. Okay, so this real valued function will also be integrable on the given interval. Okay, next we define, okay, actually this is a definition. The length of the curve C is denoted as L, which is the integral a to b absolute of z prime of t dt. Okay, the value, okay, here let me make a note. The value of L is invariant under the changes in the representation of the curve used. That is, we have just stated that the parametric representation is not unique, which means we may give several number of parametric representations to a particular curve. Okay, in what representation you are doing this differentiation and calculating this L value, that doesn't matter. Whatever may be the representation that you use to calculate the value of L, it remains the same in all possible parameterization. Okay, that is what we have stated. So now let us do more precisely. your L, if you make the that is, if we make the change in parametric representation, then L may be written as integral alpha to beta absolute of z prime of e of tau, okay, multiplied with phi prime of tau d tau. Okay, so in this case, if you can write, okay, so we may write big z prime of tau as z prime of phi of tau multiplied with phi prime of tau, just the usual chain rule. Okay, so with this L value becomes integral alpha to beta absolute of big Z prime of tau multiplied with d2. Okay, now suppose Z equals Z of t represents a differentiable arc and if your Z prime of t is non-zero anywhere in a smaller than t smaller than b, then the unit tangent vector t vector that may be written as z prime of t upon absolute of z prime of t. Okay, so with the help of a curve we are able to identify the tangent unit tangent vector to the curve itself. Okay, this may be found. Okay, this is well defined for all t in that given open interval with angle of inclination argument of z prime of t. Okay, now we shall talk more about this unit tangent vector. So when, okay, let me change the color. When this t vector turns, it does so continuously as the parameter t varies over the given interval. So what they are trying to say here is when the parameter, the value of the parameter t changes over the given entire interval, your unit tangent vector just turns. Okay, so the interval that we have considered here is the open interval a comma b. This expression is same this is the same thing that we have learned in the course on calculus. Okay, such an arc is said to be smooth. Okay, so here what we have done is that we have given the definition of a smooth curve, smooth arc. Okay, in other words, an arc z equals z of t with a smaller than or equals t smaller than or equals b is said to be smooth if z of t is continuous, differentiable, and z prime of t is also continuous. Okay, in that case, we say the given arc is a smooth arc. Okay, next we are about to define the main definition. A contour. This contour is also called as piecewise smooth arc, which is an arc consisting of finite number of smooth arcs joined end to end. Okay, now I may give you some examples of a contour and non-contour. Okay, first of all, let me give you an example of a smooth curve so that you can understand the things. Okay, if you see a straight line as a smooth curve, because in all those points on this straight line, you are able to identify the derivative. Okay, so a parabola is a smooth curve. Consider this quantity. Here, your function is continuous and it fails to be differentiable at one point at the origin. So this is not a smooth curve, right? Next, in the definition of a contour, what we are given is that it has to be a piecewise smooth arc. So you may have a straight line here, and then you may have something like this, and then you can have something like this. So this is an example of a contour. Okay, it has to be piecewise smooth. So if you split okay, if you split this interval from this point to this point, this is smooth in this interval. Okay, let me take this point to be a, this point to be b, and this point to be c. So the given curve is smooth in the interval a to b. Fine. From 0 to a it is smooth, from b to c it is smooth, but when you look at it, the entire thing, it may or may not be a smooth curve. Okay, for example, uh, okay, you just consider a curve of this sort. So from here also you may split this into any number of intervals that you want. Okay, so in whatsoever the number of intervals is, you can see this happens to be smooth in the respective intervals. Okay, and when you look at it as a whole graph, then also it is smooth. Okay, whether it is smooth completely or piecewise, that doesn't matter. If it is smooth in the piecewise, in the possible given subintervals, then we say it is a contour, right? So there are a few remarks that are to be made on the definition of contours. If z equals z of t with a smaller than or equals t smaller than or equals b represents a contour, z of t is continuous whereas z prime at t is piecewise continuous. Okay, we have seen several examples, right? So let us revisit those examples and see whether they are contours or not. Okay, the example that we have seen as a polygonal lines, this is an example of a contour. And of course, this is also a smooth curve, this is also a contour. So these, the examples, we have seen four different examples. All these are examples of contours, right? So when next is when only the initial and final values of z of t are the same, a contour C is called a simple closed contour. For this, you can consider circles as examples. Right? Next, I would like to state a theorem and end this lecture. So that theorem is Jordan curve theorem. So the points on any simple closed curve, or they may also be called as simple closed contour C, are boundary points of two distinct domains, one of which is the interior of C and is bounded. The other, of course, has to be the exterior point, right? The exterior of C and is unbounded. So, if you wish to see some examples, we are not going to prove this theorem anyway. Let me just give you the ideology what this theorem tells you. You consider a circle of this sort. Okay, now the circle, only the circle, I'm not talking about the disk. The circle is a simple closed curve. Okay, on this thing I am choosing two different points. Okay, they need not be two different points. You can choose any number of points on this closed curve. Okay, those points are the boundary points of both the regions. Here, this actually the circle splits your entire z plane into two regions. That is the region. One region may be, let me write that as region 1. So one region may be the collection of points in the complex plane such that absolute of z less than or equals 1. So another one is absolute of the collection of points in the complex plane with absolute of z bigger than 1. Okay, either we may consider this way or we may include one in the second case and exclude in the first case. These two are the possibilities. If you see what, of course, this is the thing that is said in this theorem. Okay, so this will be the boundary point for both the regions. Yes, they are boundary points for both the domains or regions that we have considered. Okay, among this, one can be the interior point. Okay, interior of the curve C and other is like if you have included here, that will come inside. If you do not include it, it will go outside. Okay, if you choose a point z equals 1, in this case this is a member of the region 2, but it is not the member of region 1. Okay, so instead of telling it as a region, we may consider it as two different domains. Okay, your simple closed contours splits your entire complex plane into two domains. Okay, you may consider some rectangles, be it open rectangle or closed rectangle, or you may consider any other shapes. Okay, rectangle, square, triangle, you may consider anything. Okay, so they happen to be true here. Actually, they'll satisfy the Jordan curve theorem. So with this, I conclude this lecture, and thank you.